Okay, let's take a look this example again, but we will apply the develop M file that we develop like this. We develop the mesh routine, and also we develop the example of the plate problem routine in order to determine the mesh like this, okay, in this sequence, okay, and we will do this problem again, okay, because we subdivide the problem to be like this, okay, so then the applied force, the equivalent nodal force is changed, okay, so this is a half of each node, right? Okay, so then this should be 9.375 and then 4.6875, but total one is equivalent with the previous that we applied just only 2 elements. Okay, so then we will use the M file that's actually, oh, sorry for this material. I just changed the M file number. Okay, you just choose CST what? Sorry, CST global stiffness number 2. Okay, CST global stiffness 2. Okay, we will apply this. Okay, so then I will clear space first. Okay, you do it again and compare with the solution. Okay, we use the CST global stiffness. Okay, and then this is just for the input file. I clear the input file for you also. Okay, for example, we may use the input file like CST example. Okay, so then supply the row of the mesh. Okay, the row of the mesh, come back to the problem. Okay, the row of the mesh, how many row? Okay, we can count the row. It's just like this. This is the first row, second row, third row, fourth row, and it's the fifth row. Okay, we have 5 rows. Okay, and we have 2 columns. Okay, 2 columns. So then, for this case, we supply M like F5. All right, M is equal to 5. In this case, M is equal to 5, and then N number of column is just 2, and the height of the plate is especially for this type of problem. Okay, in meter should be 0.5. Okay, and the length of the plate become 0.25. Okay, and we supply the elastic modulus, that is 210 times 10 power 6 kilopascal. Okay, sorry, I just missing the code a little bit. I will change. Okay, it should be kilo. Oh, yeah, that's all right. That's correct. Kilopascal. That's all right. At the first time I think it's just kilonewton. Okay, that is kilopascal already. That's all right. And then supply new disposal ratio 0.3. Okay, the plate thickness is 0.025. Okay, And this is the frame stress problem. We apply P equal to 1. Then that's all. We already have the global stiffness. Okay, the global stiffness. If you would like to see the global stiffness, you can type the capital K. Okay, capital K. You will see that we have already have the global stiffness of 36 column. Okay, that's this may be hard to find, hard to observe, right? Because it's a lot of number. Okay, then okay, the in order to check the number of the element and the coordinate of the element, you may use the output file that I already supplied to you. The output is composed just only for the mesh number. I will not create the output file for the solution. It's just for check the mesh. Okay, that's it. Supply you the element number, node number, okay, and the coordinate of each element that is in sequence that we already derived, that it should be in this pattern, right? Okay. So then you may check the element and node number, and also that is coordinate by this. Okay. After that, okay, we will solve together. We have just 5 minutes, right? Okay. So then we will apply boundary condition. Okay. So as I mentioned you before, if we set up the node like this, it's very easy to apply boundary condition because the node number is in this sequence. It's easy. So then we cut off the column and row from the first to 7. First to 6 column and first to 6 row. So then the stiffness after apply boundary condition is just for the 7 row to 36 row and 7 column to 36 column, like this. Okay. Now we have the stiffness, global stiffness after apply boundary condition already, right? And then we identify the force vector. Okay, that is for global one. It should be composed of 36 number, because it's for this problem it has 18 nodes, 2 degree of freedom per node. So then we have the total nodal force is equal to 36 member, right? This is for the global one. Okay, and after that, the global force number 36. Okay, number 36. What does it mean? Number 36. Because this is the node number 18, right? And the applied force is in y direction. It's in y direction. So then it should be the last one. Okay, this is the applied force of the node number 18 in y direction. So it is the last component. And for the 7, node number 7, it should be this 8 is the 36, right? 35 is for the force at node number 18 in x direction, that is becomes 0, right? So then this is should be 34 and this should be 32. Okay, so then the force at node the force at the force number 36, it should be 9.375 over 2, right? Okay, we already know. And for node 34, it should be 9.375. And for node number 32. It should be half also, right? Okay, then we will observe the displacement right now. In order to solve the solution, we have to apply boundary condition to the force also. It should be F. That's only 7 to 36 column row, sorry. And then we determine the displacement. And then we have the displacement right now. Okay, this is the displacement. This is from node number it should be node number 3, node number 4, right? Okay. It should be node number 1, 2, 3. It should be 0, right? And we should have the displacement from node number 4 to the last one, that is node number 18, right? Node number 18, and we will focus on the displacement at in y direction, right? So then if we consider the displacement in y direction, so what do you think? Okay, it still has like this. Okay, this is displacement in y direction, right? For the last one, it is 0.924. This is the middle node. Is equal to 0.7049, and this is 0.7186. Okay, so what's happened? Okay, what do you think? It's still not equivalent with the exact solution, right? Okay, then if we change the boundary condition from all pin support to be at the first node, we change the pin support to be just only roller support, and node number 2 to be roller also, and node number 3 just keep it to be hinge. Okay, so what happened? Okay, and then for the stiffness that we supply for the after you have the global one, right? You may use this command. You may use this command. I will show you for this. Just change a little bit. Okay, this is just for the first one, right? And we will change this. This for all node, for all constraint to be hinge. But if we change to be the pin, it should be K11. Okay, space K13. We will identify the first row and K1 7 to 36, and then we skip to third row, that is K31. Okay, K33, and then K 3 and 7 to 36. Okay, and then we go to the last sub metric, that is composed of actually it should be connect together, right? I have no space. It should be K 7 to 36 1, K 7 to 36 3, and K 7 to 36 and 7 to 36. Okay, this is the metric K after apply boundary condition. Okay, and then we apply the force vector, it should be the same, right? Fourth vector, it should be the same. Okay, we can follow the step. But for the final, that is the force after applied boundary condition, the force vector should be the same. But the force after applied boundary condition, for this case, that is we change it to be roller, right? So then we have to add up the force at node 1 and node 2 also. The force at node 1 and node 2 is become 0, right? For the case of roller. Okay, so for this case, the force after applied boundary condition is equal to F11. That is, it should be become to 0, right? And we keep F31. Okay, we eliminate the second row. Okay, and after that we keep 7 to 36 row. You all right? This is for the force that we apply boundary condition, and then we can solve for displacement. Okay, so then let's take a look what's happened to that. Okay, I will do it in short. Okay, I will do it in short. Okay, so what's happened? Okay, we have the global stiffness we already have. That is before apply boundary condition, right? The global stiffness. Okay, and we will identify it again. Is equal to what is sorry. And then last one, 7 to 36 column. 7 to 36 row is the first column, and 7 to 36 row is the third column, and then 7 to 36 row and 7 to 36 column. Okay, this is the okay. And after that, we will change the force. Okay, we will change the force. Okay, F is the global force. It should be the same from previous, right? Okay, but the force after applied boundary condition should be changed. It should be F11. Okay, and F31. Okay, and the last one is F7 to 36. It is a force vector, right? And then we find this vector is equal to so then I will show you. So what do you think? Now It is a solution. Help me to compare with the exact one, please. It is displacement, right? Displacement in y direction that is equal to for node number 18, 17, 16 in y direction. You have the solution identical to each other. Is 1 times 10 minus 5. Okay, the exact solution is what? Again, please, is equal to 3000 rate times L. L is 0.5 divided by 216 E6 is become the exact solution. (7.142857143) times 10 minus 6. What do you think? So, is this a mesh problem or not? Is it a mesh problem or not? Actually, this case is not a mesh problem when we compare with the exact solution. It is a boundary condition problem instead. Okay, you see that when you apply the correct boundary condition, that is, will be close to the exact solution. For the exact solution, this equation, you have to understand that this equation is based on what? We imagine the member like the line element, and we fix it, and we apply the force to here. Okay, we assume it's just only the line member. Okay, but now we consider the plate. Okay, and we include what? We include the Poisson effects. Nu is equal to 0.3. So then it's already correct for this case that if we apply the pressure to the plate, okay, so then we have the extension, right? And then actually according to the Poisson effect, so the member should be deformed in y direction also. Okay, that for this case, the exact solution cannot predict our result for this case if we just consider the problem like the line element. Okay, that's why the solution that we try to work out is not close to the exact solution. Okay, but when we just change the boundary condition a little bit, okay, we change from this, we constrain just only this point, and this point we have we apply to be lower. So what happened is mean that we allow the plate to be deformed in vertical direction also, right? We allow it, we not constrain it. Then what's happened to that? For this case, you will see that we have the solution of the axial displacement is identical to the exact solution every point. Okay, and we also has the vertical displacement that you see, you may observe by yourself. The vertical displacement for each node, that is a line on the plane, the same surface, that is the top surface, it should be the same like this. Okay, this is the Poisson effect. Okay, this is the Poisson effect. So then for this example, I would like to mention that actually the finite element is not only the discretization problem. Okay, discretization, in order to use the file mesh, you will get the good result. That's all right. Okay, but sometimes you have to identify the problem correctly also, in order to get the solution that is close to the thing that you would like to mention to. Okay, that's very important. So then the question is, you may try it by yourself. Now we use 20 element, right? So then what's happened if we come back to use just only 2 elements with this condition? What do you think? The solution, it should be good or not? It should be the same or not? Do you want to try? Okay, we may solve it together in short. Okay, we may solve it together in short. Okay, I will do with the 2 elements in order to show the effect of boundary condition instead. We will do it again. Okay, so this is the exact solution, right? I will create space ET and should be how many we supply ET already, right? Okay, then we should use K1. Okay, K1 is equal to what? K1 in this case. K1, I will do it again. Should be 0, right? 0 and 0.5. 0.25, 0 and 0.25 and 1. It is K1. Okay. K2. K2 is become, it should be 0. And it should be 0.5. Okay. It should be 0.25 and 1. Okay. This should be all right, right? Okay. Then we have K2 already, right? And then we assemble. I will identify KK in order to not replace the big one that we already solved. 8 by 8. And should be 1, 3, and 4, right? Do it again. Should be K2 and 1, 3. Okay, we already have the global statement. And after that, we do the same thing. I will use should be what? We have KK already, right? Okay, so then it should be KKK, right? Okay, should be like this. Okay, is equal to KK. Okay, 3 to 6. Okay, and 3 to 6. Apply boundary condition to be hidden. Okay, like this. Okay, 3 0 6 column. Say K for the third row to sixth row and fifth column. And after that is for K 8 column 8 to sorry, row number 8 and column 3 to 6. Okay, and then last one. It is a statement. Okay, we have this, and then F, it should be identified by this 5.375 BFF. Okay, and 0 and 9.375. Okay, 0 0. We have to add the force at node 1 and 2 also. 1 and 4, sorry, 1 and 4. Okay. So for this case, we add the force in x direction of node number 4. Okay. And this is the force. And we find displacement is equal to K. FF. Oh, sorry. Should be some mistake. I go faster, so then please allow me to check. Okay, the statement should be all right, right? Okay, then we have a little bit mistake for this identify the boundary condition. We supply KK instead. Okay, now this. Oh, sorry. It should be all right now. Okay, we have the statement after apply boundary condition, and then we find the displacement. Displacement is equal to what? Is equal to KKK. That FF, right? Okay, should be all right. Okay, sorry about the mistake. Okay, next slide. FF. Okay. Let's find the solution. Okay. Okay. So then you see that what's happened. This is the exact solution, right? So then that means that if we just apply the correct boundary condition, that should we can obtain the solution correspond to the exact one that we would like to predict. So then in finite element, okay, not only the finite mesh that we have to consider, the number of mesh, number of element that we have to consider. We have the important thing that is maybe more important, that is the boundary condition, and identify the problem correctly in order to compare the result that we would like to check. Okay, to simplify everything, you have to concern about the what we should do for identify the problem in order to get the better solution. That is all for this example. Okay, are you all right?